So I feel kind of like the odd man out because you guys are very familiar, I think, with a lot of the things you've already talked about. Hopefully this is new, or some of you may know some about LED lighting, but I can tell you that I will never look at a green space or the side of a roadway again without thinking about all the knowledge and science that goes into what's planted there. I used to think, well, it's there because they want it to look pretty, you know, aesthetics. But there's a whole lot more that goes into that, and that's something I certainly have learned today. Okay, which one do I do? Oh, spacebar. So, you know, we're going to talk about LEDs, and, you know, where do you begin? So, not knowing what your background is as far as what you know about LEDs already, it's kind of going to be a little kind of the basics on how do you build an LED fixture, what's it look like. Certainly, there's a lot of product out there, shapes, sizes, landscape to, you know, pole mounted fixtures, but I'm going to kind of get into the basics here. And if you have questions, certainly, you know, holler at me. But why all the excitement about LEDs? They're very energy efficient, obviously, as you've heard. Very good lumen maintenance. Gary just mentioned that a second ago. Depreciation on standard traditional lamp sources depreciates pretty rapidly over time. Did you have a question? Oh, rapidly over time. LED stays pretty constant for the life of the LED. And I'll mention a little bit more about life a little later on. Very long-lived, 100,000 to 300,000 hours. Environmentally friendly. Fixtures typically are built with components that are not hazardous substances. Small point source, and I actually did bring a fixture with me. I just happened to have it in my car. I didn't plan, but then I thought, you know what, I'm going to go ahead and take it in. But you've got a lot of point sources where typically you might have one lamp or several 4, 5, 6 lamps in a fluorescent fixture, or an outdoor fixture. You may have 1,000 watt or 400 watt or 250 watt HID fixture. This has a lot of point sources in it. Okay, so you're working with a lot more point sources, which gives you the ability, as you can see by the reflector here, that you can control each individual point source and be very precise on the lighting pattern that's being projected from the fixture. If you look at efficacy of the fixtures, you know, incandescent, halogen, mercury, all the way up to high pressure sodium, as from older fixtures or older lamp sources to more modern lamp sources, they got more efficient, more lumens per watt as time went on. LED now picks up typically about 100 lumens per watt and is now extending outward. There are some LED chips that are getting 200 lumens per watt. Again, it's the cost of the chip, manufacturing the fixture, versus the cost of maybe more lesser lumen per watt chips. But then again, it's the cost of the package and making that package affordable to the industry. Looking at this light source, you're probably very familiar with high pressure sodium. On the right-hand side, left-hand side is a traditional either metal halide or could even be, in this case it is LED, but obviously a color difference there. We're going to talk a little bit more about that later, but as you look at this, you're going to gravitate towards maybe the left side of the screen because it looks brighter. Well, I can tell you that the right side of the screen is actually the brighter side. It's how your eyes actually see the light that's there. So you're probably, I would say in this picture, you're probably 30 or 40% brighter with the right side of the screen. So what is an LED? LED is a light emitting diode. And it's a semiconductor, electrical energy through a positive and negative charge at a junction point provides heat, which photons, and then light. So this is the only thing I have in listening to Bill and some of the other presentations. This is the only thing I have that grows. All right, this is a silicone wafer, and this is what is used to produce an LED chip. It looks like a CD, very similar concept, but that is a growth, if you will. Oh, sorry. So you've got this very small LED chip that's covered with some type of a plastic lens. So just a very basic construction of what a chip actually looks like. You've got a heat sink behind the chip. There's a lot of materials in this very, very small area. Basically like the clicker end of your pen is about the size of the LED chip, but you've got all this going on in that area. And that's very scientific, and I can't tell you what materials those are, but it's all about dissipating heat, and yet at the same time producing as much light from that energy that's inside that point. So as you build a fixture, whether it's a landscape fixture or a pole-mounted fixture, you've got power coming into the fixture. You're going to have a driver that's going to drop that incoming voltage down to a power amperage that's going to be sent to the fixture. It's a lower voltage, obviously. You've got heat management, which again, LED, you're trying to dissipate the heat and protect it from any moisture. So you've got a heat management system. It's typically in the form of fins, or in this case, on an outdoor fixture, it could be the housing itself. A lot of metal surface there used to dissipate heat. You've got your array of LED chips, and then in many cases, you've got the optics or reflectors around the chips to make it provide the right light pattern so that that fixture will do what you want it to do, whether it's a floodlight and you want it to be very tight or wide pattern, or if it's an area light, whether you want it to light from the perimeter of a lot in, or if you want it to provide light in all directions. So point source allows highest efficiency. On the left, you've got a typical 150 watt metal halide, 10,000 lumens, and some of these terms you might not be very familiar with, but a lumen is just a measurement of light output. 10,000 lumens, HID, in the way of metal halide, high pressure sodium, aren't necessarily as efficient as they should be. In this case, you're using about 40% of that lamp light output through the lens and delivering 4,000 lumens. So you've got a lot of energy, a lot of potential light output, but not all that light is reaching the source, reaching the area that you want it to light. LED, however, is basically, if you've got 4,000 lumens, it's 90% efficient, or sometimes a little higher. So you're getting most of that light that's generated within that fixture is reaching your source. So again, 10,000 lumens, not very efficient. So to make LED lighting viable today, you want to get the maximum light out of the fixture. Typically, you can, as you could saw from the previous slide, you can typically design a project to a lower light level and still get the light output that you would have gotten with a traditional light source. So you want to take advantage of those characteristics. You've got great optic control, you've got great lumen maintenance, and you've got that slide that I showed you earlier where you had the high pressure sodium versus the white LED light. You've got a brighter appearance. You know, you're going to gravitate towards that white light. Not always the best choice depending on what you're lighting, but for outdoor applications, typically, you know, a higher color temperature is good. So as a project is being designed, you're looking at a light level, and typically there's an initial output which is represented by the. So you basically have an initial output which is represented by the 1, and if you're designing a site or a roadway, you're required in a lot of cases to have a certain light level. So and that is based on usually a maintained level. You've got the initial level where if you turn that lamp on, let's say it's a metal halide fixture, you're going to get X amount of light out of that fixture. But over a period of time, it's going to degrade. So you have to take that maintained level and make that's really what I'm shooting for, is the maintained level. So with an HID fixture, you're going to have an initial output, and And this also shows over a period of time where because of the life of the lamp, your HID fixture is going to burn about 20,000 hours and it's going to have to be replaced. You're going to replace it, again, another 20,000 hours, and so forth. Every time that's happening, it's depreciating, right? So you're dropping down to basically half the light output than your initial lamp was giving you when you first turned it on. With LED, you've got a much slower degradation. And just to give you an idea on the difference between lamps, the way the lamp manufacturers measure life of a lamp, if you've got a fluorescent or an HID lamp, or even a traditional incandescent lamp that you used in your lamps at your house, if a manufacturer has 100 lamps, and I'm talking Sylvania, GE, the people that actually manufacture the bulbs, if they had 100 lamps and they burn those lamps, when half of those lamps are completely out, that's the life of that's what they say, okay, that's the expected life of that lamp. Well, for traditional metal halide, 20,000 hours, half of those lamps are going to be out. And it varies depending on the wattage, but just if you took a 400 watt metal halide, 20,000 hours. LED doesn't work that way. LED, if you've got 100 LED chips and you burn those chips, whenever all of those chips are still burning, but they're only giving you 70% of that initial light output, they're considered end of life. So what are you going to do with your fixtures? Are you going to take them down and replace them? No, you're going to let it go, right? But that's how the chip manufacturers or the industry in general says that, that's how we're going to measure the life of an LED fixture. So LEDs degrade much slower than a traditional HID, as you can see from the chart. So one thing you're able to do then is design your initial foot candle levels at a much lower, if you needed 100 foot candles to be your standard initially with HID, you can actually drop that down to a lower light level as your initial, because it's going to degrade much less over time, and you're still going to reach that average mean lumens over the life of that fixture. IES is a group that provides standards for the lighting industry. LM79 is something you're probably familiar with. It's a measurement of measuring light. You've probably seen photometrics on projects that give you light levels so that you know how bright something might be. One of the things that you're required to do to create an LM79 report is there's a lot of testing that goes on, right? So you have to test that fixture. You have to know how much light's coming out of that fixture in all zones. LM80 is a report that's provided by the chip manufacturer. We manufacture light fixtures. We buy the chips. But LM80 is something that's given to us by the chip manufacturer. And from that point, we take the chip, build a fixture, then we test that fixture, which then gives us our photometric LM79 report. So this is a typical LM79 report. It basically tells us a complete light fixture, tells us how is that fixture going to perform. So what you're looking at here on the left is a photometric chart that tells you, if you can see it here, there's 10-foot candles here. There's, can't read that, but 5-foot candles, 1-foot candle. As you go further out from the fixture, each of those squares represent a distance based on mounting height. And then there's another curve that's provided with the LM79 that gives you basically every zone of that fixture, whether it's this zone or this zone, that tells you what kind of light is coming out of that fixture. From that report, you can generate I guess I thought I had a photometric report, but you've seen the reports where you've got foot candles that'll show maybe a typical parking space or a roadway that would have different foot candle levels. And that's all generated from that LM79 report. The LM80 test report, given to us, the manufacturer, from a chip manufacturer, basically says this chip is going to perform a certain way, and we've tested it under two temperatures, 55 degrees C and 85 degrees C, and then one other temperature that chip manufacturer, in this case it's 105 degrees. Nichia is the chip manufacturer in this case. So we take that chip and this information, we test it in our fixture as it's designed as the finished product, and we determine what is our temperature of that fixture specific with that chip in it. And then they give us a formula that allows us to extrapolate the life. Okay, you talk about life of the fixture, how long is it going to last? So we have to take our specific fixture, which is called in situ testing, using their chip, the information they've provided, and provide a report. And this is based on IES TM Test Method 21 and tells us here as an industry standard is what that fixture is supposed to do as far as the life of the fixture. Now there's two reports that are generated from this test method. We take our in situ temperature, which is 61.5 degrees for that specific fixture, and there are two reports. There's a calculator report and a standard report. The standard report basically takes that chip. The chip manufacturer's already tested it for 6,000 hours, and you're allowed to extrapolate that out 6 times. So you've got 36,000 hours. You know that chip's going to last 36,000 hours. Well, there's another formula that allows us to calculate as a manufacturer out further based on our temperature rating of that fixture. So that's how you get the longer life expectancy. Do we really know for sure what that life is going to be? No, but I mean, there's a pretty good, we all have a pretty good idea that they're going to last a long time, right? So based on this formula that IES, the standard for lighting manufacturers, uses, that we can extrapolate out and determine, hey, we've got a product here based on our in situ testing that's going to last X amount of hours. And you can see from a lot of different reporting, you can see where fixtures may last 100,000 hours. They may last 300,000 hours based on this reporting method. And again, it just goes back to heat management with that particular product. The other thing that you're able to do very well, and we talked about the optic assembly and reflectors, is you're able to control where the light goes very well, even better than you could with traditional light sources, because you've got so many point sources that you can control individually. In this case, you're looking at basically a forward throw. If you've got a perimeter fixture, a roadway fixture, you're wanting most of that light to be on the road. You might want a little backlight, but you want most of it to be on the road and spread horizontally. In this case, you've got a fixture that's giving you almost as much forward light as backlight, but with good control, you can also get that light that you're using behind the fixture, you can pull that around and put it in some other areas, again, based on having the correct reflectors on each chip. So the other thing that comes into play when you're looking at LED is color temperature. We saw the slide earlier where you had high pressure sodium and the LED, the two comparisons. You can do the same thing with LED chips. You can make them warmer as opposed to cool. On the left side, you've got a very cool color temperature, 6,000 degrees Kelvin. And on the right side, you've got 5,000. Obviously, you see the difference there, just in 1,000 degrees. Typically, just for comfort and looks, we try to stay within the 5,000 or below. If you're doing a classroom indoors, you may even be down to 3,500. You see the warm white fluorescent tubes. Those typically, they can come in all color temperatures, but typically for comfort for an indoor environment, you're in a warmer color temperature. Outdoor, cooler color temperature up to a certain extent, and again, not too warm or not too cool, but just cool enough to where it looks good.
Is that station really smog pro?
What's that?
Is that truly smog pro? Maybe that station?
Oh, yeah. That's what it says. I never picked that up before. Smog check, yeah. So as a typical, and Gary mentioned, we've done some of the turnpike and some of the rest areas, a lot of service stations that are there as well. This one isn't there. This is actually down in Cincinnati, close to where we are. But it just gives you an idea whether you're designing a new area or you're retrofitting an existing area. that you can go into an area where, in this case, you've got traditional lamp sources. Those are probably 320 watt metal halide, 17-foot candles, and you can replace it with, well, they're 400 watt metal halide. 460 watts is the burning wattage for a 400 watt lamp. Replace it with 115 watts worth of LED, but yet the difference doesn't match the wattage savings. Obviously, the LEDs are brighter. Again, the color temperature plays into that. You've got a much cooler color temperature here than there. There also, you've got lamps that have degraded somewhat. They're probably really only giving you 50 to 70% of their initial light output. So there's some things that go into play there as well. Site after upgrade. So the big thing about areas like that where you can either retrofit or design with LED initially is the energy savings that you would save over a period of time. In this case, annually, the $4,800 for that site. And we went from, what was it, 17 or 19 foot candles and increased that to 35 foot candles under the canopy. On a retrofit, they're always interested, well, what's my payback? How long is it going to take for me to get my money back on my investment? And in this case, you're looking at less than a year and a half. So crisp white light versus, again, high pressure sodium, LED. You can produce the warmer temperatures with LED, but in doing so, you give up lumens per watt, because if you go back to that slide very early on where you had a lens over the actual LED chip, as you warm the color temperature up, you have to, kind of like a fluorescent lamp, you have to coat the inside of that chip with some type of product, phosphor or whatever. In doing that, you lose light output. So when you go from a cooler color temperature down to 4,000, 3,500 K, you lose lumens per watt, become a little less efficient. They're still very, very much better than traditional lamp sources, but again, as you look outside to lighting, freeways, roadways, parks, rest stops, typically color isn't something that you're that concerned about. You want it to be as cool as you can be to get the most lumens per watt, but yet not be uncomfortable or in the blues like you saw with the 6,000 K. Yes?
Why are the cooler temperatures a higher degree?
Yes.
Cooler.
Yeah, and it's, I think there was a slide earlier that I kind of went by, but there was like a black body radius that had all the complete color spectrum. And I don't quite understand how that works, but when you get into higher temperatures, it's producing a cooler light.
More like sunlight.
Yes, yes. And you've also got color temperature, which is 3,500, 4,000, 5,000, and you've also got something else that goes into play, which is color rendering index, which is if you're looking at something that's red or very bright, and you go to a cooler color temperature, it's not as crisp as it would be with a lower color temperature. And the CRI is really what plays into that, because as you go higher in color rendering index, it becomes crisper. So it's kind of the opposite, CRI versus color temperature. I know that's confusing, but there's a lot of things that go on. And the point to all that is, as you look at lighting product, you have to make sure that you're looking at more than just how much light are you giving me. There's a lot of other things that go on behind the scenes as far as color temperatures, efficiencies, what's the testing that's done. Always ask for the proper reporting that's been done by the manufacturer. Design Lights Consortium, Gary, is that something you guys? Okay. So DLC is a manufacturer as well as other reputable manufacturers. As we design and look at product development, we're always trying to match or meet the DLC design criteria that's put out there, because we know that if our product meets DLC, then we've got customers out there who will be interested because of the rebates and the grants that are out there and available for products like that. We've got over 2,000 fixtures on the DLC list. Other manufacturers, have a great number of product on there as well. But their thought is that, we need to be on that DLC list. We need to make sure that as we design products, DLC is very strict as far as the criteria that they tell us, a manufacturer, how to build that fixture. It's got to have the right color temperatures. It's got to have the right CRI. It's got to have the right lumens per watt. So as you look at DLC product, you can be assured that that product is performing in a very efficient way. I've got a variety, to end the slides here, I've got a variety of different applications, whether it's area lighting, as you can see here. And I saw in some of the other photos earlier that some of the product in there was some of the product that we manufacture, actually this fixture here. But whether it's a high, in the previous slide, probably a 24-foot pole versus lower scale poles, here's a typical roadway application. Daytime and nighttime. And again, you're not stuck with a fixture that looks futuristic. Certainly we have product that looks very LED-ish, if you will, but we also, have to remember that there are other people involved in choosing what that fixture wants to look like, and as in architects and designers. And so we do have product that looks more traditional, but yet does provide that LED source. Here you've got not only the area lights, but the bollards that are shown there. And I believe this is the last slide. You've got a couple things here. You've got the bollards, but you've also got a flagpole light that's shown right there, pointing up and away, lighting the flag above. So I guess I leave you with I know this is maybe new to a lot of you, but as a manufacturer, we probably provide in our manufacturing facilities, which fluorescent, metal halide, traditional incandescent, and LED, we're really about 50-50 right now in building and selling product, LED versus traditional light sources. And that continues to weigh more on the LED side as we move on. So LED is becoming more affordable. You've seen LED fixture prices drop dramatically in the last several years, where it now becomes, for even a fluorescent product, it's really, do I want to go fluorescent? Do I want to go LED? There's not that much of a difference between the two sources. And when you think about the maintenance side of things with LED, where you can install a fixture and hopefully never have to touch that fixture for another 10 years, then you start weighing in lamp replacements, ballast replacements, the cost of exposing or disposing of those components, and just the maintenance involved in getting out there and getting up to that fixture. So